Good morning, everyone. Welcome to the IvS. Good morning, everyone. Thanks, Cleo. Welcome to the IvS seminar today. Today we have something a little bit different. We have Fleur Seuren from the Royal Observatory of Belgium, who will come and give us a talk about gravitational waves in the fluid cores of planets. Fleur began her physics career in Twente, in the Netherlands, in mathematics career in Twente, in the Netherlands, and then did her master in astronomy and astrophysics here, or also in mathematics, sorry, and then has moved to the Royal Observatory of Belgium. So hopefully be a very interesting talk. Thank you.
All right. Can anyone hear me through the microphone? Okay, great. I'll grab this. Thank you all for coming and listening to me talk about planets for once instead of stars. This might be more usual here. So today I will be mostly talking about gravito-inertial waves in planets. And I'll start because some people might be familiar with this, some people might not be familiar with this, with answering some questions about these gravito-inertial waves, and mainly important ones: what are they, where can we find them, how can we find them, and perhaps most importantly, why do we care? So, interesting. Okay, I don't know if it doesn't work. The PDF. Okay, and then, all right, so I have to do it by hand. That's fine. Yeah, so you could already read a little bit about what I think gravito-inertial waves are. Basically, there are two words in the title, gravito and inertial. And gravito is for gravity or density stratification, and inertial is for in the rotation. So basically, when I talk about gravito-inertial waves, I'm thinking about waves that are supported in any medium that has both a stratification and density, so it's stable against convection, and it's under rotation. In other words, those waves are restored by both the buoyancy force, which comes from the stable stratification, and the Coriolis force, which comes from the rotation. And finally, that also means that they will both depend on the rotation frequency and the buoyancy frequency. But as you know, it might differ. When I talk about gravito-inertial waves, I usually talk about the solutions to this set of equations, a linear version of the Navier-Stokes equation, where indeed you can see that in the top line, which is the momentum equation, I have both the Coriolis force in red and the buoyancy force in orange. And I make some assumptions on this set of equations, and I will quickly highlight them. So first, I assume that I'm in a steadily rotating frame. So if I'm looking at a medium that rotates with a constant speed, you won't see any movement. But if the medium sometimes differs from the standard speed, you will see some movement at the boundaries. Second, and this might be a bit might not unfamiliar to you, I use the Boussinesq approximation, which basically means that I assume that the Boussinesq approximation assumes that perturbations in density can be neglected everywhere except for the buoyancy force. And the Boussinesq approximation also implies that the fluid is incompressible. And those two mean that actually we filter out all P waves, which some of you might be familiar with, but in the equations I solve, you won't find those solutions. And finally, I'm using a diffusive fluid. So viscous on the top and thermal diffusion, and it's usually represented by what I call the Ekman number, because usually I will talk about dimensionless equations. And the Ekman number, Ek, is a dimensionless number that gives the ratio between viscous forces and Coriolis forces. So when it's very big, that means that viscosity is very important, rotation not so much. When it's very small, it means that viscosity is less important and rotation very much. And in the planets that I will talk about today, we'll see that this Ekman number is typically very small, which complicates it a bit. Now, you know the equations, but then if I solve that for a certain set of parameters, I will see something that looks like this. So this is a meridional cut of a sphere. So if you have a sphere I fill with fluid, I cut it from top to bottom, and then I look at the kinetic energy. The light regions are when there's high kinetic energy, and the low regions, the black regions is where there's low kinetic energy. And I want to point you towards two characteristics of the gravito-inertial waves. Hope this also. Okay. Well, you see that there are some yellow lines. So you can see like almost some straight lines through the medium, which we call internal shear layers. And if you're talking about gravito-inertial waves, those yellow lines are where kinetic energy is maximal, but they're also a bit curved, which is characteristics of the gravito-inertial waves. If, for example, I neglect any stratification, okay, and I'm just talking about inertial waves, so I was talking about these lines, then those will be straight instead of curved. Another characteristic of the gravito-inertial waves is that you see that the kinetic energy doesn't go throughout the entire medium. There are two regions where you basically don't see anything, and that's because those equations of gravito-inertial waves, they introduce what we call turning surface between where you have solutions and where you don't. And this is one of the reasons why I use viscosity, because if that turning surface is in the fluid domain, as it's here, then it's not guaranteed that you can find any smooth diffusionless solutions. And finally, I mentioned in the beginning that the gravito-inertial waves depend on both the rotation frequency and the buoyancy frequency. So this is what it looks like if the frequencies are ordered like this. So if the frequency of the wave is smaller than the buoyancy frequency and the rotation frequency, then I get something that looks like this. But if those might be in a different order, it can look differently. So they really depend on those two frequencies. Now, where might we find them? I already said, basically in any type of medium where you have density stratification and rotation. So here, you will mostly talk about the radiative regions in rotating stars, and I hope I'm saying this correctly, but that's usually the gamma Doradus stars and the slowly pulsating B stars. But also, for example, where you might, in the sun, has a radiative interior. We can't see in there, but there might be a region where we do have some gravito-inertial waves. And then for planets, also wherever I have both density stratification and rotation, I might find gravito-inertial waves. So internal layers in the oceans, in the atmosphere. But today, which I highlighted, I will be talking about the fluid core and then stable layers at the top of the fluid core, so between the boundary of the fluid core and the mantle. And then I will mostly talk about buoyancy profiles that look a bit like this. So I have here a typical profile that I might use if I solve these equations for the buoyancy profile. And in this case, I have a planet that has an inner core at 0.4, compared to the outer core radius and outer core, of course, at 1. And then the Brunt-Vezelen frequency, or the buoyancy frequency, at the inner core will be 0, which approximates a neutral core of where convection might be possible. And then it slowly transfers to some value of the buoyancy frequency at the outer core. And I can control this profile by 3 parameters. I can specify where I want the transition to be. In this case, it's 0.7. I can specify how wide that transition is, how smooth it is. In this case, it's very, very smooth. I might make it much stiffer. And finally, I can also say how strongly stratified it is. So I can give a value for the value of the buoyancy frequency at the top of the core. All right, and then finally, perhaps most importantly, not yet, how do we find them? So I use the code Cori, which is developed by my supervisor, who's over there, Andres. And that's an eigenvalue solver that solves the linear Navier-Stokes equations. And because I said I use linear equations, and also it solves it in near spherical boundaries. And in very simple steps, of course, there's a lot more computation involved. What we do is we have the equations that I just showed you. Then we make those non-dimensional, so that we can control. Then we have a spherical harmonics expansion in the horizontal direction. And because we include the full Coriolis force, that means that we can solve for each n independently, but all the harmonic degrees L are coupled. So we have to solve them all together, which is different from, I think, some stellar oscillation codes, but it does mean that we can find all rotational modes. And next that another cool thing about Cori is that in the radial direction we have ultra-spherical polynomials, and that makes sure that the matrices you use are very sparse, so we can solve very quickly and lots of sets of equations very quickly, so you can look at a very big parameter space, which is very helpful for the things I'm trying to do. And then now, after all, the most important question, why do we care that there are gravito-inertial waves? Basically, we don't know what's inside planets, we also don't know what's inside stars, but we know that there are some things that excite waves in the star. And then I just said that the gravito-inertial waves will depend on both the rotation frequency and the Brent-Weseler frequency. And then if I observe it, I can say something about those two. Now, for planets, that will mostly be because the terrestrial planets that I look at, we know the rotation very well. So we really want to know something about what is the structure of the Brent-Weseler profile. And that. All right. And I already said it twice. I will be talking about terrestrial planets today, and I will talk about two. One very close to the Sun, Mercury, and one where we're currently on, the Earth. Then starting with Mercury, because a nice thing about the planet Mercury is that it has a very thick and a very strong stable layer at the top. There are two reasons that we think that, or that it's quite commonly accepted that that's the case. The first is due to the observation of the magnetic field. So Mercury has a very weak field and also mostly not axisymmetric. And the dipole is slightly offset from the center, so not at the equator. And those three things mean that there can mostly just be solved if you have a very strong stable layer at the top. Like here, this is an example of where they did a dynamo calculation to get such a magnetic field, and then they needed this stable layer to attain that. The other reason that we think Mercury has a strong stable layer at the top of its core is because if you plot the thermal evolution, because it's not so big, that means that after a very fast time, the heat flux will become sub-adiabatic, and that means that you have a stable thermal, at least thermally stable layer at the top of the core. Here's an example of such a thermal evolution model, and you see that very quickly you already have a conductive region at the top. Now that we know, we want to excite some, or I want to see if we can excite some waves in it, and in this case I look at waves excited by the libration. So Mercury, aside from having this stable layer, also has a very peculiar rotation, because it's very close to the Sun. Every 3 days that it spins around its own axis, it also spins twice around the Sun, so it's in a 2-3 spin orbit relation. And that means that, and due to the gravitational torque of the Sun, it experiences librations. So the rotation rate is not constant, but throughout one cycle over the Sun, 88 days, if you look at it and you subtract the the constant rotation, you will see something like this. I'm very much exaggerating now, but that's what you see. So you see an 88-day periodic variation in the rotation rate. And that's what we use as a boundary condition to excite some flow in the model we have. And I actually remember that I say Corey can solve for near spherical boundaries, and that's what we solve here for the spherical boundary, but because Mercury is also not exactly spherical, it's slightly triaxial, we look at two forcings from the boundary. So the first is the most straightforward, so I just approximate this movement of the triaxial ellipsoid by the same movement by the sphere. But then also, because I have this triaxiality, the radial coordinate will move sort of in and out of the spherical boundary, which we can approximate by a radial forcing in and out of the boundary, an m=2 forcing. And then I can see what kind of flows I excite. So, something like that. It's a very big figure, so I'll try to explain it slowly to make you understand everything you see. So, at the left side of the figure, we have the case of Mercury without any stratification, so just a neutral core. And on the right side of the figure, so the other side, we have the case of Mercury with stratification. And then at the bottom, I have the case where I excite this flow from the boundary. In this case, it's m=0, but m=2 will look something similar. And at the top, those are the eigenfrequencies of the model. So if we don't force anything, but then what possible responses could you have? Now, the first thing you might notice is that on the left side, the top and bottom look very similar. So on the left top side, you see basically an inertial wave. Like I said, you see now that there are straight lines of the shear layers. And then if I have a forcing from the boundary, that will resonate with that inertial mode. So the flow structure will look very similar to the inertial wave. The case with stratification, in this case, the stratification is very strong. It's about 100 compared to the rotational frequency. The Boyne's frequency is 100 times the rotation frequency. Then we see something completely different. And actually, you might see three regions here. So, oh, this is the wrong one. So, near the inner core boundary, the Brent-Väisälä frequency is 0. So in that region, I'm still in the inertial regime, and I can see these straight lines that go throughout the entire equator to the poles. But then if the Brent-Väisälä frequency starts to increase, I get into a more gravito-inertial regime, which is here. And then I see, if you see here, more curved lines appearing, and also they can't go all the way to the poles anymore. And then if I increase my Brent-Väisälä frequency even further, I get to be where there's no radial motion possible anymore, so I just have very low amplitude oscillations. And then what happens if I try to excite something from the boundary, the amplitude is too low to excite that mode, and the flow will just stay near the outer boundary. So if there's a stratification, we actually do not see a gravito-inertial wave, but we can still say some interesting things. So first question I asked, can we see this kind of flow if we look at the measurements of the libration? So like I said, Mercury librates, and this can also be measured, can be measured from Earth, can be measured from space. And when it excites a flow, can it then change the rotation of mantle further? But I need something to couple from the flow to the mantle. It's the same as if I have a coffee cup and I would just spin very hard, like inside the water. It doesn't actually change the cup itself because there's nothing changing the motion of the water or the coffee to the cup. So I either look at some coupling mechanism, and we look at viscous coupling, so entrainment of the fluid, or electromagnetic coupling, where the magnetic field lines are stretched, and that is what might drag the mantle along with the flow. And also, I'm only interested here in m equals 0 components, because due to the nature of the spherical harmonics, any other components, if I integrate over the boundary, will just automatically be 0. So, can we change the libration amplitude by this flow? And it's a very simple answer, no. In this figure, I plotted both of the torques. In yellow, it's the viscous torque, and in red, it's the electromagnetic torque. And the solid lines are computations I did. And on the x-axis, I have this Ekman number, which I told you about. So the ratio of viscous to Coriolis forces. And the Ekman number for Mercury is very low. It's 10 to the minus 13, so we can't actually reach that with the methods we have. But I can reach quite broad from 10 to the minus 10 to 10 to the minus 6. And then I've extrapolated it to what it would be if that behavior continued to the conditions of Mercury. And then it turns out that in both cases, the torque that this flow excites is about less than 0.101%. So that really doesn't matter. But actually, that is a very good thing, because the measurements of libration are used to infer things about internal structure. For example, it was used to prove that Mercury does have a liquid core. And in those calculations, it's usually assumed that the core flow does not change the libration amplitude, which is what we actually prove here using these computations. And then, can we see something in a magnetic field? So we told you that Mercury's magnetic field is mostly axisymmetric, but there's also some non-axisymmetric part. And I have one example plotted on the left. And you see that it somehow has a bit of a m equals 2 structure. So in this case, we'll look at both. And of course, any flow of any magnetic field signal that's excited by this type of flow will be 88-day periodic, because the excitation mechanism is 88-day periodic. So the induced magnetic field that is induced will also be the same periodicity. Okay. So, actually, fun to tell, this was not in first instance what we were looking for. It was just something that we suddenly didn't understand. So again, I like putting lots of information in the plot. So at the top, I have the situation without stratification again, and at the bottom, I have the situation with stratification. And then from left to right, it's the m equals 0 component, m equals 2, and m equals minus 2. Now, the interesting thing happens for the m equals 2 component with stratification. So without stratification, basically, it happens what you would expect. So I have here different lines of the Ekman number, and blue is high viscosity, gray is low viscosity, and I see that the less important the viscosity is, the less flow there is excited, because I can't drag along that much fluid. But very funnily, this does not happen in m equals 2 component, where the kinetic energy actually increases very strong. And that's interesting, because we know the Ekman number is very low for Mercury, so then there might be a flow excited with a high kinetic energy. And where does that actually come from? Which you can see here, it's actually that they're in the case with stratification, so that's again on the bottom compared to the top, we have a very strong horizontal flow near the outer boundary. And that makes sense if you remember what I showed earlier, that the stratified layer sort of prevents the radial flow. But now, in m equals 2 component, we actually have a radial inflow. So we have something forcing a radial into a region that doesn't want any radial flow. So the stratified layer then sort of converts this radial flow into a very strong horizontal flow. And that flow has a 2-2 structure with 2 big vortices. And then the question is, can this flow induce a magnetic field that is strong enough that we might observe them? There's a new a satellite mission going to Mercury at the moment called Bepi-Colombo. And the answer is in maybe. So I did here the same for the torques. I made some computations that I could do for Eggman numbers that were reachable, and then I extrapolated what I think it would be if we actually had the Eggman number of Mercury score. And I did for m equals 2, m equals minus 2, and 2 values of the Brent phasor frequency, so very strong with the big lines and less strong with the thinner lines. And I plotted what this magnetic field would look like at this radius, which is at the top. And again, you can see a magnetic field structure that has this characteristic Y22. But the amplitude of that magnetic field, if you extrapolate it towards Mercury score, is around 1 nanotesla for a Brent phasor over 100, which is already some. So that is just about observational precision. So depending on if we have strong enough, so it would have to be a really strong stratified layer, we might be able to observe this, but not in all cases. Which brings me to the conclusion. So I looked at two things. The torques induced by the librationally-induced flow are too small to affect the rotation. But if we have a strong enough stratified layer, we might observe some structure in the magnetic field. And then we go a bit closer to home, we go to the Earth. And it might surprise you to know that while in Mercury's case, we're very sure that there is a layer and also that it's strong and thick, in the Earth it's actually a little bit of a debated topic. In almost every area of science around the Earth, geomagnetism or seismology, you will have both researchers that think it should be there and other researchers that say, no, it shouldn't be there. I'll give two examples. So mostly the reason that we think there might be some very thin, very weak stable layer at the top of the core is and due to seismology, where they found something called SMKS waves, which might indicate that there's a region of different density and different velocity just below the core mantle boundary. But again, other researchers might not agree with that. And on the left, there's actually a counter argument. This is our dynamo simulations, and on the y-axis, it is the chi-square parameter, which somehow says how close the dynamo is to the actual magnetic field observation. In that case, they conclude that it's only close when you don't have a stratified layer. But of course, they only use very low, very high Eggman numbers, whereas the Eggman number for the Earth is something of the order of 10 to the minus 15. So it's still up in the air, but of course, would we be able to observe a gravito-inertial waves, which we haven't yet, but then we could end the debate, but that would be the dream. So this is a plot of what's, and I like it because it can explain you very quickly what kind of wave motions they're usually thought to be in the Earth score. So on the x-axis I have the frequency, and on the y-axis the damping, and you see very clearly three regions, and those all have names. So on the bottom right, that's where the inertial waves are, but we're not really interested in them because their periods are very short for what we're looking at right now. And then you have in the middle, it's what's usually called torsional Alfvén waves, which are columnar modes, and they have equal magnetic to kinetic energy. And on the right side here, you have MC waves, or magnetocoriolis waves, which have dominant magnetic energy. And then if I add a top stratified layer to this, I basically can call all of that Mach waves, magneto, Archimedes, Coriolis waves, because now I have three forces to contend with, the Lorentz force, the buoyancy force, and the Coriolis force. So how do we figure out what's actually happening? And of course, the good thing, or the bad thing, depending how you look at it at the Earth, is that we have a lot of observations. In particular, we have a lot of observations of the magnetic field, especially the secular variation, so the first derivative of the magnetic field, shows some interesting oscillations, and we have variation in the length of day. And both of those can also go back a long time, though with less data points. And the goal is, of course, to find a set of waves that explain both of those at the same time. And what's usually being done is that you have the magnetic field near the core mantle boundary, and people invert that for, using some assumptions, and then try to see if that matches the some common signal in the length of day variations, so the change in rotation in the Earth. And especially like what we are looking for, there is a 6-year signal, which is which is common between the magnetic field and the LD variations, and a 60-year signal, a bit longer. And there should again be enough a mechanism that couples the flow to the mantle. So and it's usually assumed that that will be the electromagnetic torque. So the waves you find should have a sufficient electromagnetic torque. And of course, there's lots of people looking into this, and I listed some of them. So on the one hand, people assume quasi-geostrophy, so they make the dimension a bit smaller, that they assume that there's no motion next to the rotational axis. So, but there are also other people that did the same thing for Mach waves, so with a stratified layer, and then only looked at the stratified layer itself. And what I wanted to do, or what I'm currently doing, is looking at the types of waves that we can decide in the full core, so 3D, and with both the non-stratified part and the stratified part together. And then, so again, this is ongoing work. I see something like this. So in the middle, it's basically the same plot as I showed earlier, but then I've neglected all the inertial waves. And I see again the two regions of the torsional waves and the MC waves. And then on the left side, I put a very sharp, very thin layer on top of the core, and on the other side, it's a very smooth and very thick layer. And you see in both cases, mostly that the torsional waves are not really affected by this stratified layer, but the interesting thing happens with the MC waves, that they decrease in damping, and they increase in frequency, and they even increase in the magnetic torque, which means that they actually become more important for connecting these magnetic field observations and LOD variations. So that's the status now. But one thing we need to take care with is that in this case I'm looking at eigenfrequencies, because it's also not really known what excites these motions, mostly assumed that it will be convective motions that excite these waves. So we have to take care that the amplitudes are actually correct, because usually if you just plot an eigenmode, then the amplitude will be random, so it doesn't actually say anything about how big the magnetic torque is, for example. But that's what I'm currently working on. And then another thing that we are trying to do, which is a small teaser, which might be more to your standards, is about, for now, a Bussy next-sum. But the plan is to very quickly have the anelastic approximation to get somewhere closer to stars and also gas giants. And this actually started with a poster that we saw at the American Geophysical Union, where this is a dynamo simulation in the sun, where they pointed out that they found something which they call Rossby waves. Rossby waves, for the time being, that are a type of inertial wave, so waves without the stratification. But what we think these waves shouldn't actually exist in the radiative core, because Rossby waves only exist in a very thin shell. They are just horizontal waves, so they shouldn't have been found in a dynamo simulation of the sun, where the radiative material is very big. And I can actually prove that and show why we can still find them. So on the left side, I'll start with the horizontal lines in this figure are the frequencies of the Rossby waves. So the frequencies that were just pointed out in the other figure. Then on the left figure, I varied inner shell radius. So you can see what I promised, that only for a very thin shell, you actually have waves at those frequencies. And then if I increase the shell radius, those waves disappear. So for a very thick shell, they shouldn't exist. However, we know, or we've seen previously, that the stratified layer doesn't like, or stratification doesn't like radial motion. So in effect, it might be that that forces the motions to be a bit horizontal again. And we tested that. And indeed, if you create strong stratification in the sphere, you bring these Rossby waves back again to their expected frequencies. But now they're in company of more waves with different radial nodes. And that might be interesting, but there's one thing that's, I said it before, a bit sad about the radiative material in the sun, is that it's sheltered by this very big convective envelope, so we can't actually observe any of this. But, and that's still work in progress, so it's more of a teaser, then it might, we might still say some things. So this is, all those points are, and on the x-axis I have the Brent-Weseler frequency, and on the y-axis the frequencies. And in this case, I'm not looking just at the radiative interior, but on the radiative interior with a convective envelope, but still a Bushinesque sun. So on the left side of the figure, basically the Brent-Weseler frequency is very small, so we might as well not be there. So you're just looking at a convective full. But then on the right side of the figure, you do have some radiative interior, and there you can also find these Rossby waves again. So where these are here. But we see that even though the radiative interior can't be observed, you can see that some inertial waves do change their frequency because there is something going on in the radiative interior. And that might be something that we can observe. But that's still early stages, so much more to come. And then I just would like to thank you. And I hope that you've been paying attention, because this is indeed that Gravito-inertial wave that I showed earlier. Thank you very much.
Thank you, Fleur, for the really nice talk. Are there any questions?
Thank you for a lovely talk. When you do the spherical harmonic expansion in the horizontal direction, and you solve the linearized equations, how do you figure out which solutions correspond to which modes?
It's a bit, well, knowing which frequencies you expect, but also it's just actually plotting the modes and seeing what they look like. So it takes some time, but yeah, you already know like what the frequency should be. I can look at the magnetic energy, the kinetic energy, and then figure out from there what I would call that. But I think if you ask the question, as you should know, naming waves or oscillatory motions is a bit tricky, because for different fields, people might call the same thing differently. So it's harder than you think, but yeah, we just look at the modes themselves.
Thank you.
Any other questions?
Tons of questions, like usual. And thank you for plotting the transversal velocities. as I keep asking you in your progress meeting. But my question is on the sun. So if you go back 1 or 2 slides, because the waves are observed, huh? So let me...
Yeah, the raspberry waves at the
Yeah.
surface. But these are, because this is this is a plot where they just took a slice just below the tachocline and then plotted the radial vorticity. So these raspberries are, and I think she also showed that if they go further, they might change into something else. So this is specifically in the radiative material. But there are also raspberries on the surface, yes.
Yeah, so that's my question, because if they are at the surface, they have to tunnel through the convective layer, right? Whether we like it or not.
Yeah.
And so that convective layer is rotating differentially, and we know how it rotates from helioseismology. So my question is, are you, with your methods, able to deduce if, and if so, how rotation helps waves tunnel through the convective layer? You see my question?
Yeah. So right now, I think the code is like that. You just have a uniform rotation, but I think they're actually, it's also in motion, right? Unless, wasn't Jeremy working on that differential rotation?
Yes, it's in the works.
Yeah.
For the moment, the rotation is in motion.
Yeah.
But we have some preliminary work to include the differential rotation so that is actually plotted.
Which is actually why we were able to match these things very nicely, because they also show that because of the tachocline, the differential rotation only goes through the convective envelope, and in the radiative interior, it's just a uniform rotation. So then we could match them very well. But of course, that changes when you add the convective envelope.
So can you crank up the rotation to our stars, please?
Any other questions? Oh, Janus.
Thank you so much for the presentation. I have a very basic question. When you showed the periodicity of the libration of Mercury, I saw that at the top it was quite flat. In the bottom it was sharp, but at the tops it was always like... and I was just curious why that is. Either that or I need a new glass prescription.
Yeah,
so at the top it looks a bit flat. Do you know what I mean compared to the bottom?
Yes. I don't actually know exactly what that means. This is, I actually haven't seen that before, so that's a good observation. But
Wow, I amazed myself. Thank you.
yeah,
Okay.
also, but the thing is that the red lines in this are just the what they assume is the libration, but the black dots, those are actually the measurements that you are used to find.
Yeah, I was just wondering if it's something periodic. What would make it? Well, I don't know. Yeah, stop and then dip again.
Yeah, well, very nice observation. I am going to look into that.
No worries. I'll Google it.
Thanks.
Hi, thanks for a nice talk. So, I mean, looking at this plot, I think also one thing you notice is that it seems the data is very sparse, and you were mentioning Bepi Colombo. I'm wondering, will that help, like, fill up this plot, for instance? Like,
Well, so as you can see, for one, this is a plot from 2007. So this is done strictly from radar measurements for the Earth, and this is where the first big paper where they said, oh, we've seen this libration measurements, so there is Mercury has a fluid core. But in the meantime, we have had some satellites that went there, so we have, I think now we do have much more measurements, and they're also starting to use these measurements to see if we have a solid inner core and like constrain how big that would be. So, this is a while ago.
Yeah, this is already prehistory. Thanks.
Any further questions?
Hi, thanks for the talk. I had a question about Boussinesq approximation, especially about the incompressibility that you assume, because you said it suppresses P waves, but I was just wondering, does it also not have any influence on your results for your gravito-inertial waves? Or?
The thing is, which is also like, I'm looking at terrestrial planets, so in that case, the Boussinesq approximation, while not exact, is still a quite good approximation. But that's precisely the point why it sort of fails if we move towards gas giants or stars, because then it's not that good of an approximation anymore. So yeah, it does influence, but in our case it doesn't matter because it's a very good approximation for what we're looking at.
Okay, thank you.
Yeah.
Further questions?
If my eyes spotted it correctly, you have about a factor 100 difference between radial and transversal displacement. Did I see that well in Mercury?
Could be.
So,
Yeah.
Yeah?
I think even more.
Right.
Yeah.
So when you say kinetic energy, you just ignore the psi theta squared, or how?
No, the kinetic energy is the total, so
you do square the two components in the velocity.
Square all of the components.
Okay.
But this is well also not. If I'm strictly correct, this will not be the exact amplitude. It will be the like if I take the kinetic energy and then the
modulus. Yes.
Yeah, the modulus. So.
But it's only a few. Yeah, I was just wondering if all your plots do that. As you should. Yeah. Okay. And then the obvious last question: how can we translate this to stars?
Yeah, I think that's what I tried to end it with. I think for one, as I just pointed out, we do need to get rid of the Boussinesq approximation, but that is very close to being done. And then except the thing that we can do is really look at these rotational waves, and which might be very interesting. And also I showed just some examples here of the waves where I have a radiative interior and a convective envelope, but we've also seen, like in things that we tried, some radiative envelopes and convective interiors, and then we could actually see this. What I think you're also starting to observe, that you couple in some cases the inertial part with the gravito-inertial part. So we did see some examples for that, and we might work with that further. But yeah, once we get rid of the Boussinesq approximation.
Are there any other questions? If not, I think we can thank Fleur again for a lovely talk. Thank you all for coming, and see you next week.